Hello, this is my English speaking this is my English speaking practice, and I solve coding problems on LeetCode, and today I will work on this problem, gray code. Okay. Okay, let's take a look at the problem statement. An n-bit gray code sequence is a sequence of n power of n integers where every integer is in the inclusive range. The first integer is 0. An integer appears no more than once in the sequence. The binary representation of every pair of adjacent integers differs by exactly 1 bit. And the binary representation of the first and the last integers differs by exactly 1 bit. Given an integer n, return any valid n-bit gray code sequence. Okay, so this is the definition of n-bit gray code sequence, and the key thing is the binary representation differs by exactly 1 bit. So for example, we should take a look at every pair 0 1, 1 3, and 3 2, and 2 0, and the every pair binary representation of every pair differs exactly 1 bit. So this is 0 and this is 1, so differ by 1 bit, the first digit, and this is 1 and this is 3, so differ by 1 bit. Okay. And the n is from 1 to 16. Okay. Exactly 1 bit. And we return any valid n-bit gray code sequence, so there might be several valid gray code sequence. but basically there is a range like this, so I guess the number in the output array might be consecutive. Yeah. So that means we can increment one by one. Differs by exactly 1 bit. Okay, I see, but 0, 1. Yeah, let me think about the binary representation for 3-bit. 0, 1, 2, 3, 4, 5, 6, 7. That's it. And exactly 1 bit differs. Yeah. When the number is 2 of power n, for example 2 or 4, it increments a digit, so it means they differ. They differ more than 1 bit, and and the adjacent number like 135 is differs exactly 1 bit. But the problem is how to find the next number that differs exactly 1 bit. Yeah, but I have an idea. Difference 1 bit means difference of 2 power of n. So that means we can choose 101 or 011. Yeah, that is 5 or 3. Yeah, and basically we scans from the smaller one, so we think about changing 0 to 1. So in this case we think about this case, only this case. Okay. And the gray code sequence must start with 0. So 0, 1, 0, 1. 0, 1, for example, 0, 1, 3, 2. No. Yeah, probably difficult, but how to create a cycle because it must be 0 at the first integer. So in this range we can choose increment 1 or 1, 2 or 4, right? 1, 2 or 4. Yeah. And we have these numbers and we use this, and so yeah, we can jump to 1, 2 or 4. Okay, but after jumping to 1, we cannot jump to 2 because the 1 is already used, so we cannot change this bit. So from here we jump to 3 or 5, right? Yeah, 3 or 5. And to make a cycle, 1, 2 or 4 must be adjacent of 0. How to pick? Maybe 4 and 1, 2. Three, 5, 6, 7. Yeah. Two, 3, 7. Okay. Is there any patterns? We have to count the number of zeros. means like this. So 0, 1, zero, 1, 3, 2, 5, 7, 6, 4, 0. How about this? 0, 1, 3, 2, 2 to 5. It's not good. 2 to 6. Okay. 2 to 6. 6 to 7. 7 to 5. 5 to 4. 4 to 0. Okay. We can make it. But I don't know the pattern, how to implement this. The idea that counts the number of 0 is good. I think this is good. So and the every transition is determined by these values 1 to 4, 1 to 4. So we can choose any of numbers in the next depth, and which is 2, for example. And in this case we can move to 3 or 6 because the difference is 1 or 4. Yeah. Or we might move to 4. How about this? 0 to 4. 3, 4, 3 is not good. I see. There is a restriction. So two power of n. Mm, yeah. So we have to care about 2 4 2 4 just 2 4. Mm. Zero 2 4 5. Oh. 5 2 3 is also not allowed. How to determine which can be and which not can't be? I got tired. Oh. Oh. I gave up. Let me see the solution. Wow. Gray code is a binary numeral system where two successive values differ in only one bit. This property is crucial in hardware design and encoding schemas to avoid transitional errors, especially in systems sensitive to signal changes. Instead of brute forcing combinations, we can directly generate the gray code using a simple and elegant formula, like this, where I is the integer value or an integer number. The code I exclusive OR and the number I that is right shifted. The number right shifted I. This formula works because the most significant bit, MSB, of the gray code is the same as the most significant bit of the binary number. Every subsequent bit in the gray code is computed by exclusive ORing the current bit and the previous bit in the binary representation. You might study this in an electronics related subject in your graduation or high school. For example, converting binary 100110 to gray code, keep the first bit 1, then XOR each bit with the 1 before it. What? 00110 00110. How about this? This one 10011. Okay. And the result is 10101. So the final gray code would be 110101. 110101. And the gray code I is 110101. 1 What? One, two, three. 3-bit differs. Is this correct? I cannot understand. The code performs exactly the logic. 3-bit differs. What? In this case, 2-bit differs. Huh? I'm not sure. I'm not sure. Zero, 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 zero. One, two, I see, I see. Okay, so okay. When the input is 7, we want to find the When the input is 7, we want to find the gray code of 7, and that differs from the gray code of 6. But why? I'm not sure. But the gray code is always differs 1 bit when they are consecutive. Okay. Is an ordering of the binary numeral system such that 2 successive values differ in only 1 bit. For example, the representation of decimal value 1 in the binary would normally be 001, and 2 would be 010. In gray code, these values are represented as 001 and 011. That way, incrementing a value from 1 to 2 requires only 1 bit to change instead of 2. Gray codes are widely used to prevent spurious output from electromechanical switches and facilitate error correction in digital communications such as digital terrestrial television and some cable TV systems. The use of gray code in these devices helps simplify logic operations and reduce error in practice. Many devices indicate position by closing and opening switches. If that device uses natural binary codes, position 3 and 4 are next to each other, but all 3 bits of the binary representation differ. The problem with natural binary codes is that physical switches are not ideal. It is very unlikely that physical switches will change states exactly in synchrony. In the transition between the 2 states shown above, all 3 switches change states. Invention. In principle, there can be more than one such code for a given word length, but the term gray code was first applied to a particular binary code for non-negative integers. The binary reflected Frank Gray introduced the term reflected binary code in his 1947 patent application, remarking that the code had not as yet no recognized name. He derived the name from the fact that it may be built up from the conventional binary code by a sort of reflection process. In the standard encoding of gray code, the least significant bit follows the repetitive pattern of 2 on 2. The next digit a pattern of 4 on 4. Okay. The binary reflected gray code list for n bits can be generated recursive from the list for n-1 bit by reflecting the lists, listing the entries in reverse order, prefixing the entries in the original list with the binary 0, prefixing entries in the reflected list with binary 1, and then concatenating the original list with the reversed list, for example generating the 3 n equals 3. Reflected. Oh. What? One. What? It's okay. Yeah, I gave up this problem. But yeah, I understand the concept of gray code, which which is one of the encoding the numbers, and the gray code differs in the gray code, 2 successive values differs in only 1 bit, like this. Okay, and this is the formula. This is the formula for encoding in gray code. So yeah, I remember this formula. Yeah, but I don't know why this is the why we can achieve the gray code. But I understand the concept of gray code and the formula. So So I will finish this problem. And right now I'm so tired, so sleepy, so I finish this stream. Thank you for watching.